Now we can deal with the slightly more complicated situation of capacitors in series. What I have right here is a battery of voltage difference delta V total, which is connected in series to three capacitors, C1, C2, and C3. They're in series. So what's going to happen in this situation is the battery is going to push positive charges out this way, out that way, like that, and we'll get some charge on their positive Q. I'll label it Q like that. And then what that's going to do is that's going to push the positive charges off of this side. They'll be pushed over here to there. Same amount Q though, and these positive charges being pushed to there will of course abandon these negative charges right there. So this is also Q. And then these positive charges will push these positive charges away to over here, leaving negative charges right here. Or you could also say that these attract the negative charges. And finally, what we're left with is negative charges over here. Now, although I did that in a seeming chronological order, you must realize that really that all happened at the same time. The positive charges left this end and went into the negative terminal of the battery all at the same time as these other positive charges went there and went out to this side, as all in the same time as all the charges migrated to where they currently are shown in this picture. So this situation can be analogized with a situation like this. Notice that our battery right here, that's kind of like something that gives energy to charges. So let's imagine that as an elevator. Let's say I've got like 4 positive charges in this elevator, and the elevator does work on the charges to lift them up to this level right there. So now the charges have been lifted up to a higher altitude by the battery, and they're now up here. 1, 2, 3, 4. So the charges are up there, and of course they don't want to stay in the elevator. They want to spread out. They end up pushing away and ending up right here. And what I've got right there is this situation right there. That is just a wall, like kind of a traffic barrier or something. The charges cannot leave that spot. They can't get past that barrier. They'd love to go downhill. They'd love to travel downhill like that, but they can't because that barrier is in the way. What does that correspond to over here? Well, here's my charge. They can't go across this because this is an insulator right there. Cannot carry current, so they'd love to go downhill, but they can't. So what happens is, though, that over here, that pushes positive charge over here. These positives are right there up against that wall, and it kind of leaves those negative charges right there. And I'll just draw these on here as we go. Negative, 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 negative. That's where the negative charges are. Negative, 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 negative. And that leaves these positive charges over here, and a bunch of negative charges right here. And let's draw all those in as well. Now notice down here, this level right there is the ground. Hey, that works out pretty well because it is the ground. This represents like the bottom end of the battery right there. So it's just like that is the lowest level that they reach, the ground level. And if I could free up, if any of these charges could get loose, in fact, sometimes we have what's called breakdown, where our capacitor becomes a conductor. If the voltage gets too high, anything can become a conductor. So you could have a situation, if the voltage was too high, where one of these positive charges escaped and started rolling down the hill. But in normal operation of the capacitor, we do not have that happen. They're just stuck here in this situation like this. So you can see that these charges are at the highest potential, these charges are at the lowest potential, and you can see that there's a potential difference, in other words, like an altitude difference between each of those plates. So here's the one thing you can guess. The total altitude difference, in other words, the distance that the elevator lifts up, which corresponds to the delta V total caused by the battery, how do these delta V's add up to the delta V total? Well, looking at this diagram, you can kind of tell, how do these height differences add up to the total height difference? This is like delta H total, or I'm just going to call it delta V total because that's really what it is. How do each of the height differences add up? These do not have to be the same capacitor. These could be different height. The way I've drawn it here, it looks like they're equivalent capacitors. They don't have to be. But we see that the total drops, I'm going to call this delta V1, this is delta V2, this is delta V3, and this is delta V total. What's the relationship there? Well, if you see that delta V1 plus delta V2 plus delta V3 have to add up to delta V total, then you got the right idea. And that's all we're going to need for our derivation. Now, I can express this delta V right here using my famous equation, caps are quite overvalued, as a different way. Now, one thing we do have to notice is that how does the Q on this capacitor compare to the Q on this capacitor? Well, it's exactly the same. Q is identical or the same for all caps in series. If they are in series, Q has to be the same. Because what happens is any Q that's been pulled off of this right here, any Q that's pulled off this last capacitor and goes to the battery, that's how much charge the battery has to add to this capacitor right there, to this one there. So the Q's must be the same. It's not physically possible for them to be any different. We know Q is the same. Delta V may be different, but here's what we can do. We know that Q is the same for each, so I'm just going to express it like this. Delta V1 can be expressed using this equation. How can we express delta V1? Well, that's simple. Delta V1 is just Q over C1. And this is Q over C2, and this is Q over C3. The charge is the same for all. So what this all means is, just because this delta V total, just like this, the whole height difference has to add up, these three have to add up to that, I'm going to write it like this. Well, let's just stop right there. Now, one thing to understand is, what is this delta V total? Well, that would be the Q over the C equivalent. Now, let me show you what I mean by that. What is the equivalent capacitance of this system? Well, the way to see that is this. This is what the equivalent capacitance that this battery sees is. It doesn't know what's going on in the circuit. All it knows is that it puts charge Q right on there, and that'll be negative Q over here, and it's got a voltage difference between these two outer plates. That's delta V total. That's the voltage difference between the top of the battery and the bottom of the battery, delta V total. So from the battery's perspective, there's only two plates. The plates that it deposits those charges on, and the plate that it pulls the positive charges off of, with the two plates being delta V total apart. So this is the C equivalent of that the battery thinks is going on. In other words, if you just replaced all those capacitors in series with one C equivalent, the battery would not know any difference. So here's what this gives us. This C equivalent, which I'm going to express as, I'll write this again to just remind us of this, delta V total equals delta V1, not shown here, delta V2 plus delta V3. We don't see the individual caps, but this could be expressed as Q over C equivalent. And this will equal Q over C1 plus Q over C2 plus Q over C3. And notice the Q's are the same for each. They can cancel, which gives us our final result of this, which is just 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. Notice that it's very similar to the equation for resistors, not in series like these capacitors are, but resistors in parallel. 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. I actually prefer to write this a slightly different way. And if you take this and you just invert this side, so just so I get C equivalent, here's what you get. Now what that allows you to see a little bit is that the more capacitors we add, the lower the equivalent capacitance gets. So that might say, why is that? What's up with that? Well, one way of looking at that is just this. The more capacitors we have in series, the more the voltage difference is broken up into smaller pieces. In other words, the more capacitors I have here, the more of these little hills there would be. There'd be more of them. So each capacitor gets a smaller voltage difference associated with it. The smaller the voltage difference for each individual capacitance, the smaller is the amount of charge it can hold. And again, the charge has to be the same for each one of these. So by breaking up the voltage into smaller and smaller pieces, you're actually making it a weaker capacitor. Sometimes that's what you want to do, but if you're trying to make a big capacitor, putting a bunch in series is not the way to do it.